For most of railroad history, trains didn't just run on tracks. They talked to them. Every few seconds, a wheel would drop into a tiny gap between two rails and kick back up. That sound was so constant, so universal, that an entire century of train travel is basically remembered through it. Today, on almost every main line on Earth, that sound is gone. Not reduced, gone. You can ride a freight train across a continent or a bullet train across a country and never hear a single click. So how did an entire global industry eliminate a design feature that had existed since the very first railroads? A feature engineers spent decades insisting was structurally necessary, not optional. And why did it take a chemist's happy accident, a fatal disaster, and one very strange piece of engineering logic, spread out across nearly a century, to finally make it disappear? To understand that, we have to go back to why the gap existed in the first place and why removing it looked, for a very long time, like a good way to derail a train. Steel expands when it heats up and contracts when it cools down, and it's not a small effect. A 100-meter length of rail changes size by roughly 1.1 millimeters for every degree Celsius it swings. Push that across a full year, a scorching summer afternoon, into a freezing winter night, and a single rail wants to grow or shrink by inches. Early railway engineers in the 1830s understood this, so they designed around it. Rail was rolled in short, fixed lengths, roughly 39 feet in North America, 66 feet in Britain, and bolted end to end using perforated steel plates called fish plates or joint bars in the US, usually 4 to 6 bolts a side. A deliberate gap, sometimes with oval bolt holes to allow the rail a bit of room to slide, was left at every single joint so the steel had somewhere to go when it expanded. It worked in the sense that it kept rails from destroying themselves in the heat, but it also meant that a railroad wasn't really one continuous structure. It was thousands of short structures, chained together, with a weak point built into every single link. On a single mile of North American mainline in the jointed rail era, that meant something like 140 separate joints per track, each one a tiny impact zone. American railroads staggered the joints on the two rails so wheels didn't hit both sides at once. European railways more often lined them up directly across from each other. Either way, joints are where the railhead gets hammered down by repeated wheel impacts. Joints are where fatigue cracks start at bolt holes. Joints are where speed has to be limited, because a wheel dropping into a gap thousands of times per mile puts enormous repeated shock loading on both the train and the track. For most of the 20th century, the majority of a railroad's maintenance budget went toward fixing the same few feet of track over and over at every single one of those joints. Which raises the obvious question, why not just weld the rails together and remove the gaps entirely? Because for decades, almost everyone assumed that would be a disaster. The tool that eventually made welding rail possible wasn't even invented for railroads. In 1903, German chemist Hans Goldschmidt patented a reaction where aluminum powder burns with iron oxide to release enormous heat, a process he'd originally developed to extract pure metals. He realized the same reaction could melt and fuse steel in the field, using nothing but a crucible and a mold clamped around two rail ends. Thermite welding was born. Around the same period, American engineer Elihu Thomson was independently developing a completely different method, flash butt welding, which used electric current to melt and fuse rail ends together, but only worked inside a plant, not out on the open line. The first real test on a US main line came decades later. In 1932, the Delaware and Hudson Railroad thermite welded about a quarter mile of rail into one continuous piece behind its general office building in Albany, New York. It held. A larger installation followed on the Schenectady, Maine a couple of years after that. But almost nobody trusted it yet. If a rail could no longer expand into a gap, engineers reasoned, all that thermal force had to go somewhere, and where it went, they feared, was sideways, bowing the track out of alignment until a train derailed. So even on these early welded stretches, crews installed backup expansion joints anyway, just in case. Those backup joints, it turned out, never even moved. But nobody was ready to bet a passenger railroad on that yet. Britain's first serious attempt at a long welded section didn't come until 1957 on the East Coast Main Line, and it included what engineers later admitted were catastrophic design mistakes. Widespread adoption stalled for another 2 decades on both sides of the Atlantic. The real breakthrough wasn't a stronger rail or a better weld. It was a change in the question. Instead of asking, how do we give the rail somewhere to expand, engineers started asking, what if we made sure it never needed to? Here's the idea. Every piece of continuous welded rail has what's called a neutral temperature, the temperature it happened to be at the moment it was permanently fastened down. At exactly that temperature, the rail sits at 0 stress. Get hotter than that, and the rail wants to expand but physically can't, so it pushes outward with compressive force instead. Get colder, and it wants to shrink but can't, so it pulls inward with tensile force instead. Compression is the dangerous one. At just 30 degrees Celsius above neutral, a rail can carry roughly 72 megapascals of compressive stress, nowhere near the steel's yield strength, but more than enough to buckle the whole structure sideways if the track underneath isn't holding it firmly in place. Railroaders still call this a sun kink, so the fix became almost absurdly simple. Install the rail on a hot day or heat it artificially with propane burners before fastening it down, so its neutral temperature sits close to the hottest day it will realistically ever see. Some corridors in the southern United States are set at a neutral temperature above 105 degrees Fahrenheit. If the rail is essentially never hotter than the day it was installed, it's essentially never in dangerous compression. The second half of the trick is brute restraint. Every kilometer of continuous welded rail is held down by roughly 2,000 ties, each clamped by steel spring clips, all sitting in tightly packed, self-locking crushed stone. Heavier concrete sleepers gradually replace timber ones, specifically because they add mass and friction the rail can't overcome. Add it all up and the combined resistance is enough to stop the rail from moving even a fraction of an inch. So instead of turning into physical movement, the thermal force gets absorbed internally as locked-in stress, as long as it stays inside safe limits. In other words, railroads didn't defeat thermal expansion. They just made absolutely sure the rail could never act on it. Even with the physics solved, jointed track stayed in widespread use through the 1960s, largely because ripping out an entire national rail network is expensive. It took a tragedy to speed things up. On the evening of November 5, 1967, a packed 12-coach train from Hastings to London Charing Cross was running at roughly 70 miles an hour near Hither Green in southeast London. A fatigue crack had been quietly growing through a bolt hole at a single rail joint, and a small wedge-shaped piece of steel finally broke away from the railhead. The train derailed. 11 of the 12 coaches came off the rails, 4 turned onto their sides. 49 people were killed, and 78 were injured. Britain's 6th deadliest rail disaster on record. The official investigation found the joint had been poorly maintained, resting on a shallow, badly packed sleeper, and that the line's speed limit had recently been raised, without the track underneath being upgraded to match. In the most literal sense, it was a joint that couldn't keep up. British Rail's response was to accelerate what engineers had already proven possible 2 decades earlier, on the far side of the Atlantic, and in their own pre-war Albany and East Coast trials. Continuous welded rail conversion sped up dramatically across the network. Concrete sleepers at joints were banned on the affected region, and maintenance and inspection standards were rewritten from the ground up. Hither Green wasn't the only reason CWR eventually spread worldwide, and it wasn't even the first fatal accident traced back to a broken joint, but it was the one that made the calculation impossible to ignore. Every mile of jointed track left in service was, quite literally, thousands of tiny fatigue experiments running at once with passengers on board. It turned, "We should probably get around to this eventually," into, "We cannot afford not to." By the time the dust settled, the numbers made the case on their own. Southern Railway in the US had already begun installing welded rail on every renewal project around 1953. By the 1960s, most Class 1 railroads were doing the same, including a major installation on the Pennsylvania Railroad's Northeast Corridor. According to the International Union of Railways, continuous welded rail cuts ongoing maintenance costs by up to 60% compared to jointed track. Rail life roughly doubles. Jointed mainline track typically wears out after around 600 million gross tons of traffic pass over it. Continuous welded rail can push past 1,000 million. But the bigger unlock was speed. Jointed track structurally cannot support high-speed rail. The repeated joint impacts at velocity become unmanageable for both the wheels and the steel. Japan built continuous welded rail into the Shinkansen from its very first line in 1964, precisely because there was no other way to run passenger trains at those speeds safely. Every high-speed system built since, the TGV in France, the ICE in Germany, the Acela in the US, runs exclusively on continuous welded rail. There is no version of 200-mile-an-hour passenger service that exists on bolted joints. The physics simply doesn't allow it. Removing the gap wasn't just quieter and cheaper. It was the precondition for an entire category of railway that didn't exist before. Continuous welded rail is more expensive to lay initially than jointed track. The welding equipment, the tensioning, the heavier concrete ties all cost more upfront, but it pays that back within a few years through lower maintenance, longer rail life, and faster, smoother, quieter service. Today, virtually every main line in the industrialized world carrying meaningful speed or traffic runs on it. The clickety-clack didn't disappear by accident. It was engineered out, deliberately, joint by joint, over roughly 40 years. Here's the thing though, eliminating the gap didn't eliminate the physics. It just moved the danger somewhere less visible. Sun kinks still happen. When rail temperature climbs roughly 40 to 50 degrees Fahrenheit above its installed neutral temperature, the compressive stress can exceed what the ballast and fasteners are able to hold, and the track buckles sideways anyway. It still causes derailments. It still forces railroads to impose emergency speed restrictions during heat waves, sometimes across thousands of miles of track in a single afternoon, slowing down entire regional networks with no visible reason on the surface. Amtrak's own policy spells out exactly how seriously this is still taken today. Once ambient air hits 95 degrees Fahrenheit or the rail itself reaches 128 degrees, engineers are required to slow down, sometimes cutting a 150-mile-an-hour ASILA to under 100. In the summer of 2025 alone, heat orders repeatedly hit the Northeast corridor between Washington and Boston, canceling trains and stretching trips by 15 minutes to well over an hour on some of the hottest days of the year. Weather-related delays across the network totaled more than 4,000 hours in a single recent fiscal year. And the problem is getting harder, not easier. Longer, hotter heat waves mean rail temperatures now spend more time further above their installed neutral temperature than the original 20th century engineering ever accounted for. Railroads are responding with new tools instead of old ones. Union Pacific has started painting sections of rail white in its hottest corridors, specifically to reflect sunlight and shave several degrees off the steel's peak temperature. Other operators are experimenting with fiber optic sensors buried alongside the track that measure axial stress in real time, so crews can catch a section approaching its buckling threshold before a train ever reaches it, rather than finding out after a derailment. So the story doesn't really end with the gap disappearing. It ends with the same 120-year-old problem: steel wanting to move with the temperature, still being fought every single day. It's just being fought underground now, in ballast and clips and neutral temperature calculations, instead of in a bolted joint every 40 feet. The clickety-clack didn't go away because someone found a way to let the rail move freely again. It went away because engineers figured out how to hold it so completely still that the movement never had anywhere to go. Next time you're on a train and it's dead silent, you're not riding on track that beat physics. You're riding on top of thousands of tons of compressed steel, held exactly in place, one clip and one tie at a time. If you've ever felt a train mysteriously slow down on a scorching summer day for no visible reason, now you know why. Want to know why there are dozens of empty trains running every day? Watch this video next.